We learned yesterday that a polynomial of degree 2 in one variable is called a quadratic because there's a number being squared. X squared is called a quadratic expression. When we introduce a second variable and we turn this expression into an equation, we've just created a function. Recall that functions have input and output. So this rule, this equation, lets us determine what the output is based on the input. So if I put in a 0 for x, that means I'm going to take x 0 squared. My output is a 0. If I let x equal 1, 1 squared is 1 times 1, that's 1. If we put in a 2 for the input, I'm going to now square a 2, which is 4. So this ends up being a squaring function. Whatever your input is, you square it, and that gives you the output. Well, writing a table of function values is one way to display the information. Another way is to graph. So let's look at this input and output table on a graph. And let's say I've counted by ones in each direction. Well, if I plot 0, 0, it's at the origin. There's a point at the origin. There's a point at 1, 1. There's an ordered pair at 2, and then I'd go up 4. There's an ordered pair at 3, 1, 2, 3, and then I'd go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I went over 4 and up 16, I'd be off of this graph. Well, so it looks like this function is curving, and as the x's are getting bigger towards infinity, the y values keep squaring, so they keep going towards infinity. But what's happening on the other side of the origin? What if I went the other way? What if I put in x was negative 1, and then I square the input? Negative 1 squared is 1. So I end up getting a mirror image of the other point of 1, 1. I get a mirror image at negative 1, 1. If I put in a negative 2 squared is 4. So over to the left 2 and up 4. If I put in a negative 3, my output would be 9, over 3 and up 9. So as x approaches negative infinity, or as my x's are getting smaller, my outputs are still squaring. So the end behavior for left or right, as you go towards infinity or towards negative infinity, the end behavior goes towards positive infinity. So this shape is the output of this quadratic function. This is called the parent function of a quadratic because it is the most basic equation. This is called a parabola. And this specific example where we are at the origin and then we go over 1, up 1, over 2, up 4, over 3, up 9, this is the parent graph of a parabola. What we're going to see is we can have some, let's see. There are transformations. There are transformations that can change the function and therefore the graph. So if we start with y equals x squared, I can translate the parabola. I can translate the parabola vertically simply by adding a number. I'll call the number k. If you add a number k to the parent function, that will translate the graph, parent graph, vertically. For example, if I want to talk about y equals x squared minus 5, this is identical to the parent. The negative 5 translates the exact shape of the parent down 5. 1, 2, 3, 4, 5. So instead of having the vertex, this point at the origin, I now have it at the point 0, negative 5. And that relationship of from the vertex going over 1 and up 1, going back to the vertex going over 2 and up 4, going back to the vertex going over 3 and up 9, then parabolas are symmetric, so I know there's going to be mirror images on the other side. This would be the graph of the function y equals x squared minus 5. It's the exact same shape as the parent, it's just been shifted down. Y equals x squared plus 2. Guess where that's going to end up? I'm going to start up at 2, and then I'll have the shape of the parent parabola. So it's the same shape, it's just been shifted up 2. So as long as x squared stays the same and is not being multiplied by anything, you'll have the same parent shape. It'll just this plus k, whether k is negative, that moves it down. If k is positive, it moves it up.